Okay, let's go for the next topic. It's gonna be the electric potential energy. And to do that, let's compare this electric potential energy to the gravitational potential energy. Because we already covered this part and because they are similar, since they have both a conservative force. Okay, let's start with gravitational potential energy. As you know, we will have particle at position A and we'll release it later than at position B, right? So the particle is being moved because of the gravitational force. Now let's find the work done by this gravitational force. So what do we have? We have that work by definition is equals to force times delta S times cosine theta. In this case, the force is going down, the same thing as the displacement, so these two are parallel. So cosine, the angle is 0, and cosine then is 1. Perfect. So we have this force times displacement, but displacement is going to be this distance minus this distance, HA minus HB. Okay, perfect. When we plug this value right here, we create these conditions. In this case, we have mg, remember, is the force done by gravity. When we multiply these two quantities, what do we have? mgHA minus mgHB. But look, this is final position B in A initial position. We can switch them, right? Because it's better to work with the difference, the change, right? The change, remember, is final minus initial conditions. Okay, and then when we do that and we define mgh as the gravitational potential energy, we know that gravitational potential energy is defined as mgh. Okay, we apply this definition right here. Well, we have that the work done by gravity from moving a particle from A to B is equal to negative that change in the gravitational potential energy. Okay, now let's create some conditions for charges. To do that, let's create a constant magnetic field, right? The gravitational field right here is constant. Okay, let's do the same thing for charges. To do that, we use these two huge plates. Correct, there are charge, one is positive, one is negative, correct? And then let's create the same condition like right here. The electric field must be the same as gravitational field going downward. And we need a charge or particle that when it's released, it's raised downward, the same thing as for masses. And that charge is positive charge, right? The test charge. You release a positive charge right here, right? It accelerates downward, the same thing as the masses in the gravitational field. This is why it was believed before that the charges that move are the positive charges because they are related, right, to gravity. They have the same pattern behavior as when we have masses in gravity, in gravitational field. So in this case, you release again a positive charge from point A, it goes to point B. And the work is done by this electric field. The electric field is constant, the same thing as for the gravitational field in this case, correct? And by definition, the electric field is force to the magnitude. Force equals to force divided by the charge, in this case, the test charge. Perfect. Again, let's find the work done, in this case, by this field. Gonna be force times, or the force, present right here too. Okay, gonna be force times delta S cosine theta. The same thing as before, right? These two quantities are parallel, so the angle is 0, cosine 0 is 1. Okay, now we have delta S is position A minus position B. Great. We multiply, right, and we have these quantities. Now, one more time, like right here, right, we define the electric potential energy to be Q naught ES. Right? And the same thing, right, we plug the values as we did before, and at the end we have that the work done by the electric field going to be is equals to negative the change in the electric potential energy. Okay, now let's go back to this quantity right here, this definition. What happens if I divide this by Q naught and this one by Q naught? What do we have? Well, in this case, remember, every time we have a quantity divided by another quantity, we create a new quantity. We have to define it. So we divide this quantity by this quantity, we create a new quantity. And we define this quantity right? The electric potential energy divided by the charge, the Q naught, we define it as the electric potential, correct? So we have this quantity that is defined as the electric potential. So the electric potential is V equals to, is defined as V equals to the electric potential energy divided by Q naught. Perfect. But from here, if we go back to this quantity, correct, the electric potential is equals to Q naught over Q naught is 1 is going to be the electric field times S. Right? Perfect. Now, we can replace these values right here if you want to. Let me erase this part. So the work done by the electric field from A to B is equals to what? It's equals to a negative. What happens if we divide this? Okay, I'm right here. Let me go right here. Divided by Q naught right here, correct? Let me start right here. I don't have enough room. Divided by Q naught and divided by Q naught. But what is this? This is equals to negative, what is this quantity? Gonna be V, V at point B minus V right at point A. But what is that? That's the change, correct? So it's equals to the negative, the change in the electric potential, right? So we get then that this, also this is called voltage, right? This is called voltage or electric potential difference, or just potential difference, or just potential. It's the same meaning, correct? So voltage or electric potential difference is equals to negative the work done from A to B divided by Q naught. Remember, the unit for voltage is volt. So 1 volt is equals to, then 1 volt is equals to, it's a new quantity, 1 volt is equals to, what is the unit for work? Newton divided by Coulomb, right? The unit of charge, right? Coulomb. So this is 1 volt. Perfect. Now, no, not Newton, it's joules, not Newton, it's for forces. This is work, energy, newtons, okay, joules. Newton is for forces, okay. Gonna be joules per coulomb. That's gonna be the unit for this is one volt. Correct? Perfect. Now let's go to the case when we have this situation. Now we got from here to here. What should be then the change in the not the change, but this is the potential difference. So the potential difference. Now we compare this to this using this quantity right here. Correct. It's gonna be what? It's gonna be, because let me see, I erased it. Because also remember, work is equals to, one more time, is equals to this, but this is equals to, look, oh my god, I need more room. Okay, we have that work from A to B, right, is equals to this quantity, which is negative what? Negative Q naught E times S, correct, at B minus Q naught ES at A. We divide this by Q naught to get change in voltage, potential difference, Q naught, correct, and this is again Q naught. Well, what do we have is that this potential difference, which is this part now, correct, is equals to what? Is equals to negative the electric field times change in S. Correct? This is cancelled right here, this is cancelled right here, and it's gonna be negative the electric field times SB minus SA, and this is the change, right? It's equals to negative E right delta S. Okay, perfect. So this is again the representation for the voltage or potential difference, or electric potential difference, the same meaning. Great. Now let's go to the next topic right here in this section. The next topic is gonna be the electric potential due to a point charge. Okay, for a point charge, imagine that we have this positive charge right here, right? And we know that this is the electric field, correct? Going away from the charge, like in this case. And now we have a test charge at this position, and then we release it, right? And then it goes to, let's say, this position right here, correct? We have a force, and we have the displacement. We have a force acting. Now, what is the work done by? What should be the work done by this point charge? Well, the distance from here to here, remember, is now let's use r sub a, and the distance from here to here is just point A, correct? This is point B. It's gonna be r sub b. We know, right, when we have a force and displacement, these two are parallel, what should be the work done? Well, the work done one more time is equals to force times S. Well, it will repeat the same conditions right here, correct? We divide by Q naught, we divide by Q naught to find the, for example, the potential difference. Okay, now let's go back to this equation. Okay, so potential difference is equals to negative, right? The work done from A to B. But what should be that work? Equals to force, right? Force. What happens? Which quantity is changing in this case? Okay, let's do, it's gonna be force. Force times S, correct? Force times S. Delta S right here, okay, delta S. Delta S. Delta S. We'll repeat the same steps as before, correct? What else? Divided by this Q naught. Perfect. And what is delta S? So it's equals to, one more time, it's equals to negative force. And also, what is the force? The force now, for the force we use the Coulomb's law, right? Force is equals to K, Q1, Q2. In this case, this is Q, now the other one is Q naught, gonna be Q times Q naught divided by R squared. Correct? When we do this, what do we have? Well, this is equals to negative this product. And what is this product? What is the force? Equals to K Q naught times Q divided by Q naught times R sub B squared, correct? Times what? Times R B squared minus K Q naught times Q divided by Q naught R A square R A, or R sub A, right? Because we're looking for the condition at this point and the condition at this point, right? And then what is this is equals to, for a point charge, right? This potential difference is equals to what? This is cancelled with this, and we have, this is not square, the distance R, right? Remember, delta S is equals to RB minus RA, correct? The distance, perfect. Now, what do we have? We have that this is equals to negative K times what? Times the charge divided by RB minus, right, K times the charge divided by RA. Also, for a point charge, right, for a point charge, we can take this, the electric potential for point charge is equals to K the charge times or divided by the distance. Okay, and this is the difference for a two positions, correct? This is for point charges. One more time, for point charges, we have the potential difference is equals to negative k q, the charge times rb minus the constants q over r a. Correct. Now let's go back to the case when we are dealing with potential energy. Correct, potential energy. When we're dealing with potential energy, for example, when we have masses, correct? This is the ground. Ground has 0, right? Potential energy, gravitational potential equals to 0, right? And when we're going up, potential energy increases, right? This is high potential energy, this is low, right? Potential energy. In this case, energy is 0 at the lowest point. When we're dealing with charges, the same thing, right? We have that if the particle positive charges, a positive charge moves downward, meaning that it's a high potential. High potential is positive, so the positive charge, the positive plate is a high potential, and the negative plate is the low potential. And when we release the charge, right, it moves downward, it accelerates downward. The same thing as right here, right? The mass accelerates downward. So it's high potential, low potential, right? When we are doing work to move the charge from here to here, we are increasing the potential energy. The same thing over here, right? When you have an object that you move from here to here, you increase the potential energy because you are going against the field. Right? If you are going against the field, right, you increase the potential energy. Correct? Now imagine that we have one more time this positive charge, and this is fixed, and we have this another positive charge which is moving. When we approach this to this one, correct, of course the potential energy increases, like over here, right? When we move this charge to this one, we are doing work because these two repel, so the potential energy increases, right? So the same thing happens over here. The potential energy increases when you approach to this positive charge. Got it? Okay, great. So this is high potential, low potential, high potential, low potential. Perfect. Now let's go to we can have also these graphs, right? You have this positive charge, you have this electric potential, correct? And this is x, the distance in the x direction. We have a positive charge right here. So when we are approaching, right, to this positive charge, remember this is positive charge. Of course, it's the test charge. What happens to the electric potential? Well, increases, correct? Perfect. When it's negative, well, we can make the same thing. When it's negative charge, that's gonna be in opposite direction, in the bottom part, right? In that way, for negative charges. Perfect. Now imagine that we have this is the case when we have two charges. What happens if we have more than two charges? What should be the electric potential, right? Or the electric potential energy? Well, in that case, the electric potential is equals to the sum, right, of this product, K Q sub I over R sub I. That should be in the case where we have more than one particle. Okay, perfect. This is for point charges. So far we're dealing with point charges, right? Except this one. This one is in general for once we have the electric field. But this is point charges, point charges, point charges. Okay, perfect. Now let's go to the last topic for this section. the last topic for this section is gonna be equipotential surfaces. Let's do it. Equipotential surfaces. In this case, we have this example. In this is positive charge. One more time, we have that this is the electric field. This is the electric field for a positive charge. Now, let's apply this condition. Let's look for the electric field at the same distance from the charge, right? This is the same distance from the charge, imagine. It's a sphere, it's gonna be in 3D. Imagine it's a sphere in 3D. So, the distance to the charge right from this surface is the same. If the distance is the same, what should be the potential? The electric potential, right? What is the electric potential? What should be the electric potential right here? Okay, let's do it. So the electric potential, the charge is the same, the distance is the same, so the electric potential is the same on this curve, on this surface, right? Because we are the same distance from this charge and the charge is the same. So what should be this? Then the electric potential is constant along this surface because r, the radius, is constant, correct? So we call this surface equipotential surface, correct? Imagine one more time we have a surface, so the potential difference for any point between those surfaces, right, is 0, right? So the change in the potential difference is 0. Why is 0? Because potential difference equals to, let's say, electric potential, let's say at point B minus electric potential at point A. But because they are the same electric potential, so these two are the same, so the change is 0. Meaning that the electric potential is constant. And we call this the equipotential surface when we're dealing with a surface. If this is a line, we call this the equipotential line. Perfect. Now, we can have another one right here, right? Another surface. And also, it's gonna be the equipotential surface. Another equipotential surface, right? Perfect. But what is the equipotential value right here? Okay, well, imagine that this is a V1. Okay, it's gonna be V2. But which one is a higher value? V1 or V2? Well, remember, it depends on the distance. If the distance decreases, this quantity increases. So if this is, let's say, 20, this is gonna be what, 10? Because the distance increases. If the distance increases, this value, right, the electric potential, decreases. Correct? Perfect. Also, if we have a two parallel plate charges right in this way, what should be the electric field in between? Remember, it goes from leaving positive charges and goes to negative charges in this way, correct? Perfect. What should be the equipotential surfaces? Well, all the particles at this point are at the same potential, right? At this point, the same potential, right? The same potential right here, right? Those are the equipotential surfaces. What is the condition to create a equipotential surface? Well, this is a condition. The condition is that the surface must be perpendicular to the electric field, right? This is the electric field, correct? And this is, let's say, we can use surface, or we can use, right, changing position or displacement, right, in this way, right? They're moving in perpendicular direction to the electric field, correct? The electric field is the same, so there's no change in the potential energy. in the electric potential, right? So the same thing happens right here. So we have to create a surface perpendicular to the electric field. And the surfaces are those. Also remember, these are coming from this equation, right? Because in general it's gonna be the delta S cosine theta, correct? If cosine theta is 90, if the angle is 90, cosine 90 is 0, and we can also find that condition. But again, this is the situation for equipotential surfaces or equipotential lines. For example, imagine that we have a particle right here and it goes from here to here. Right, this is the displacement. Well, we can break that distance, that vector, into components. One component in this direction, one component in that direction. Correct? But look, in this direction, right, the work done is, you want to move a particle's work done is going to be 0. It's like a gravity, right? In gravity, right, this is the ground and this is a particle right here. If you move a particle from here to here the same height, the change in potential energy is 0, right? Change in potential energy is 0. Why? Because it's not change in the direction of the field. In this case, the gravitational field, right? The gravitational field goes in this direction. So it's not changed. The same thing happens over here, right? The electric field goes in this way. So it changes in this way, let's say the direction. Not changed, but the direction. And in this case, when the motion is perpendicular, well, there is not work done by the field, right? Because it's not changing the direction of the field. The same thing happens right here, right? The field is in this way, and we move perpendicular to the field, like in gravity. Well, there's no change in the energy. The same thing happens right here. So the work done is only in which direction? In this way. Only in this way. We have this angle, right? What should be then the work done the work done by the electric field in moving a particle from here to here is the same thing as moving a particle from here to here, not from here to here. Correct? So it's gonna be the work equals to electric field times, actually it's gonna be force. It's gonna be force times S. But what is force? Force equals to electric field times Q naught times well, in this case, the force that we're dealing with is in this direction, correct? Parallel to the electric field is equals to S cosine theta in general. So in this case, because the angle is 90, correct? So it's gonna be 0. It's only this component is acting. It's like in this case, right? When you're moving from here to here, only this component is acting, which is cosine. Also because remember, the forces acting are conservative forces. When we deal with conservative forces, the work doesn't depend on the path, depends only on the initial and final position. Like right here, right? Doesn't depend on this path, only initial and final position. Right? Could be this path, could be any path, or initial and final position with respect to this direction. The same thing happens right here, right? On the initial and final position. It doesn't depend on the path. Okay, and with this we finish this section on the electric potential energy. Thank you, see you in the next video.